Tonight we're embarking on a journey through the solar system, exploring what it would actually be like to live on each planet. Not the glossy, sanitized version you see in science fiction movies, but the brutal, unforgiving reality of existence on these alien worlds. So before we begin, if you enjoy these deep dives into space and science, take a moment to like this video and subscribe to the channel. It really helps. And let me know in the comments which planet sounds the most terrifying to you. Now, dim the lights, get comfortable, and let's travel beyond Earth together. Before we step foot on any alien surface, we need to understand what we're getting ourselves into. The solar system is not a welcoming place. Earth is the exception, not the rule. Every other world in our cosmic neighbourhood wants to kill you in ways both spectacular and mundane. Some will freeze you solid in seconds. Others will crush you like a tin can or roast you alive. A few will expose you to radiation levels that would cook your DNA from the inside out. When we talk about living on other planets, we're not discussing a weekend getaway. We're exploring environments so hostile that they challenge everything we know about survival. The human body evolved over millions of years to function in Earth-specific conditions. The exact pressure of our atmosphere pressing down at sea level, the particular composition of gases we breathe, the narrow temperature range that keeps our blood liquid and our cells functioning, the protection from radiation provided by our magnetic field and ozone layer. Remove any of these factors, and survival becomes a desperate battle against physics itself. Throughout this journey, we'll examine each planet in order from the Sun outward. We'll explore Mercury's temperature extremes, Venus's crushing pressures, Mars's thin air and deadly radiation, and the gas giants where the very concept of ground dissolves into crushing depths of liquid and metallic hydrogen. We'll venture to the ice giants at the solar system's frozen edge, where temperatures plummet to nearly absolute zero and winds scream at supersonic speeds. This exploration will reveal not just the scientific facts about these worlds, but what those facts mean for human experience. What would you see? What would you feel in those final moments before the environment overwhelmed you? How would each planet kill you, and how quickly? These are questions that transform abstract numbers into visceral reality. Let's start our journey on Mercury, the closest planet to the Sun. From Earth, Mercury appears as a tiny dot, difficult to observe because it never strays far from the Sun's glare in our sky. Ancient astronomers knew it as two different objects. They called it Apollo when it appeared in the morning, and Mercury when it graced the evening sky. Eventually they realized these were the same swift-moving world, orbiting the Sun faster than any other planet at a breakneck 107,000 miles per hour. Mercury completes one orbit around the Sun every 88 Earth days, but here's where things get strange. The planet rotates so slowly on its axis that one Mercury day, one full rotation, takes 58.65 Earth days. This creates a bizarre situation where Mercury's year is shorter than its day. The combination of its orbital period and rotation creates an even stranger phenomenon. From certain spots on Mercury's surface, you would see the Sun rise, stop, move backward across the sky, stop again, then continue forward before setting. This solar dance occurs because of the planet's elliptical orbit and its slow rotation, creating a gravitational resonance that locks 3 rotations to every 2 orbits. But the real challenge of Mercury isn't its peculiar motion, it's the temperature. During the day, when the Sun hangs overhead at its full, scorching intensity, surface temperatures soar to 800 degrees Fahrenheit, hot enough to melt lead and zinc. The rocks themselves radiate heat like a pizza oven cranked to maximum. The ground beneath your feet would glow dully in the visible spectrum, shimmering with thermal energy. But Mercury has no atmosphere to speak of. What passes for an atmosphere is actually an exosphere, a tenuous cloud of atoms constantly being stripped away by solar wind and replaced by atoms kicked up from the surface by micrometeorite impacts and the Sun's radiation. The surface pressure is less than 1 trillionth of Earth's atmospheric pressure. For all practical purposes, Mercury's surface is a vacuum. This means there's nothing to trap heat when the sun sets, nothing to moderate the temperature. And so, at night, the temperature plummets to negative 290 degrees Fahrenheit. This is a temperature swing of more than 1,000 degrees, the most extreme temperature variation of any planet in the solar system. The rocks that were glowing hot hours earlier are now cold enough to freeze carbon dioxide solid, cold enough to liquefy oxygen and nitrogen. Imagine trying to build a habitat on Mercury. During the day, your structure would need to withstand temperatures that would soften steel and cause thermal expansion in any material. Your cooling systems would work over time, fighting against the relentless solar radiation bombarding the planet. Then, as the long night begins, a night that lasts the equivalent of 176 Earth days, your heating systems would need to maintain livable temperatures while everything outside freezes solid. The surface itself offers no shelter. Mercury's landscape looks remarkably similar to our Moon. Heavily cratered, ancient, and dead. Billions of years of meteorite impacts have pummeled the surface, creating craters upon craters, from tiny pockmarks to enormous impact basins like Caloris Planitia, which stretches 960 miles across. The impacts have pulverized the surface into a layer of fine dust and rocky debris called regolith. This powdery surface would cling to everything, getting into seals and mechanisms, abrading surfaces with its sharp, unweathered edges. But Mercury holds a surprising secret. At its poles, in craters so deep that sunlight never reaches their floors, scientists have detected water ice. Yes, water ice on the planet closest to the Sun. These permanently shadowed craters remain cold enough to preserve ice, protected from the Sun's fury by the high crater walls. Temperatures in these shadowed regions never rise above 180 Kelvin, cold enough to preserve not just water ice but also frozen carbon dioxide and other volatile compounds. This discovery sparked speculation about using these ice deposits as a resource for future missions. Water could be extracted, split into hydrogen and oxygen for rocket fuel and breathing air. But accessing these resources would be an engineering nightmare. You'd need to work in perpetual darkness, in temperatures hundreds of degrees below zero, in a near-perfect vacuum, all while dealing with Mercury's other hazards. And then there's the radiation. Without a thick atmosphere or a strong magnetic field to protect you, the Sun's radiation hits Mercury with full force. Charged particles from solar wind, cosmic rays, and intense ultraviolet radiation would bombard anyone on the surface. Over time, this radiation would break down materials, damage electronics, and pose severe health risks to any humans present. The Sun, which provides life-giving warmth on Earth, becomes a hostile furnace on Mercury, a source of deadly heat and radiation. The lack of a substantial magnetic field also means the solar wind can directly interact with Mercury's surface. During particularly strong solar storms, the magnetosphere can be pushed down so far that the surface itself is exposed to direct solar wind bombardment. This could accelerate the weathering of any structures or equipment left on the surface, stripping away atoms and molecules through a process called sputtering. Mercury's small size, only slightly larger than Earth's moon, means its gravity is weak, just 38% of Earth's. While this might seem advantageous, making it easier to launch rockets or move heavy equipment, it also means that anything you accidentally dropped would fall in slow motion, bouncing and skittering across the rocky surface. It would affect your movement, your balance, the way liquids behave, and even how your cardiovascular system functions over time. There's also the question of time. A single day on Mercury lasts 176 Earth days. For 88 days, the Sun would crawl across the sky, baking everything beneath it. Then, for 88 days, darkness and cold would reign. Any human settlement would need to either move continuously to stay in the twilight zone between day and night, or develop systems robust enough to handle these extreme cycles. The psychological impact of such an environment would be profound. Imagine spending 3 months under constant blazing sunlight, the sun barely moving in the sky, the temperature climbing every hour. Then, just as you adjust, the sun finally sets and you face 3 months of frozen darkness. The human circadian rhythm, evolved over millions of years to follow Earth's 24-hour cycle, would be utterly disrupted. Sleep patterns, hormone production, mental health, all would suffer without Earth's familiar day-night cycle. Mercury also lacks any resources beyond the basic rock, metals, and those polar ice deposits. There's no organic material, no carbon-rich compounds, nothing that could be easily converted into food or useful materials. Everything would need to be imported or synthesized from the raw minerals present. The planet is rich in iron and other heavy metals. Scientists believe Mercury may have a relatively enormous iron core making up about 85% of the planet's radius. This high metal content could be valuable for industrial purposes, but extracting and processing these materials in Mercury's extreme environment would require technologies we haven't yet developed. Living on Mercury wouldn't just be difficult. It would represent one of the most hostile environments in the solar system, surpassed perhaps only by the surface of Venus or the depths of Jupiter's atmosphere. Every moment would be a battle against temperature extremes, radiation, and the fundamental incompatibility between human biology and Mercury's environment. It's a world of extremes where the very concept of comfortable has no meaning, where survival would depend on constant vigilance and robust technology operating at the limits of physical possibility. Moving outward from the Sun, we come to Venus, often called Earth's twin or sister planet. From space, Venus gleams brilliantly, the brightest natural object in our night sky after the Moon. Its thick cloud cover reflects most of the sunlight that strikes it, giving the planet a luminous, almost pearl-like quality that captivated ancient astronomers. The Romans named it after their goddess of love and beauty, a name that seems appropriate when you observe Venus as a brilliant point of light in the evening or morning sky. But Venus's beauty is only skin deep. Beneath those shining clouds lies the most hellish surface in the solar system, a world where the environment pushes the very definition of what's possible on a rocky planet. If Mercury is a planet of extremes, Venus is a planet of sustained, unrelenting horror. Let's start with the atmosphere. Venus's atmosphere is thick, incredibly thick. At the surface, the atmospheric pressure reaches 93 bars, 93 times the pressure at Earth's sea level. To put this in perspective, this is equivalent to the pressure you'd experience if you dove about 3,000 feet beneath Earth's oceans. This pressure would crush most submarines. It would certainly crush an unprotected human instantly, compressing your body with a force that would collapse your lungs, crack your ribs, and squeeze the air from your tissues before you had time to register what was happening. This crushing atmosphere is composed of 96% carbon dioxide, with clouds of sulfuric acid floating in the upper reaches. The carbon dioxide creates a runaway greenhouse effect, trapping heat with devastating efficiency. The surface temperature on Venus averages 867 degrees Fahrenheit, hot enough to melt lead, bismuth, zinc, and tin. This is hotter than Mercury, even though Venus is nearly twice as far from the Sun. The greenhouse effect is so powerful that the temperature barely varies between day and night, or between the equator and the poles. The massive atmosphere stores and redistributes heat so effectively that the dark side of Venus is only slightly cooler than the side facing the Sun. At these temperatures and pressures, the carbon dioxide behaves strangely. Near the surface, it exists as a supercritical fluid, a state of matter that acts like both a gas and a liquid simultaneously. This supercritical carbon dioxide ocean covers the entire surface of Venus, about 6.5% as dense as liquid water. It conducts heat extremely efficiently, helping to transfer thermal energy from the day side to the night side and maintaining the planet's uniform temperature. But it also means that the very air around you would have a thickness, a tangible presence that resists movement in ways gases normally don't. The clouds that give Venus its brilliant appearance are made primarily of sulfuric acid droplets, with the main cloud deck extending from about 30 to 42 miles above the surface. These aren't wispy, ethereal clouds like those on Earth. They're thick, opaque, and continuous, completely enshrouding the planet. The sulfuric acid is concentrated, about 75 to 85% by weight, and it exists as a fine mist of droplets suspended in the atmosphere. Interestingly, it rains on Venus. Not water rain, but sulfuric acid rain. However, because the temperature is so high, the rain never reaches the surface. The droplets evaporate in a phenomenon called virga as they fall through the increasingly hot lower atmosphere. This creates a cycle where acid condenses in the cooler upper atmosphere, falls as rain, evaporates, rises as vapour, and condenses again. It's a perpetual acid rain machine that never quite completes its cycle. The winds on Venus are extraordinary, while the planet itself rotates very slowly, taking 243 Earth days to complete one rotation, and doing so in a retrograde direction. Opposite to most planets, the atmosphere races around the planet in just 4 days at the cloud tops. These super-rotating winds reach speeds of 224 miles per hour at high altitudes, faster than any hurricane on Earth. Near the surface, however, the dense atmosphere moves sluggishly at only a few miles per hour. But even these slow winds carry enormous force because of the atmosphere's density, enough to push and buffet objects with surprising strength. The atmospheric circulation on Venus is driven by a simple but powerful pattern. Hot air rises at the equator, flows toward the poles at high altitude, sinks at the poles, and returns to the equator near the surface. This creates a Hadley cell circulation pattern that extends from equator to pole, unlike Earth, where Hadley cells only extend to about 30 degrees latitude. The intense solar heating and the planet's slow rotation combine to create this global pattern, which remains remarkably stable over time. Landing on Venus has proven extremely challenging. Soviet Venera spacecraft managed to reach the surface in the 1970s and 1980s, and a few even transmitted data and images before the brutal environment destroyed them. Venera 13 lasted just over 2 hours on the surface, the longest survival time of any spacecraft on Venus. The images it sent back showed a hellish landscape of flat, broken rock under an orange sky, lit by the sun's light filtered through the thick atmosphere. The rock on Venus's surface is volcanic in origin, primarily basalt, the same type of rock that forms from cooled lava on Earth. But on Venus, the rocks are subjected to extreme conditions that alter their chemistry. At surface temperatures and pressures, certain chemical reactions become possible that don't occur under normal Earth conditions. Iron sulfide compounds form. Carbon dioxide can oxidize iron even without water present. The rocks slowly react with the atmosphere, forming sulfate and carbonate minerals. Venus also lacks plate tectonics like Earth's. Instead, the planet seems to resurface itself catastrophically every few 100 million years. Massive volcanic events cover the old surface with fresh lava, erasing impact craters and creating a relatively young surface. The planet has thousands of volcanoes, from small shields to massive calderas. Some may still be active today, though proving current volcanic activity on Venus has been difficult given the challenges of observing through the thick clouds. The sky on Venus would appear orange to yellow, with the clouds blocking most blue light and scattering the longer wavelengths through the thick atmosphere. Visibility at the surface is actually decent when measured in Earth terms, perhaps a few kilometres, though the thick atmosphere creates a hazy, diffuse quality to the light. The sun would be completely invisible, hidden behind the impenetrable cloud deck. You'd experience a dim, perpetual twilight, with no way to tell day from night or see the stars. The temperature is so extreme that it affects everything. Electronics fail rapidly. Traditional semiconductor-based computers and sensors can't function at 8 and 67 degrees Fahrenheit. Even high-temperature electronics based on silicon carbide or other materials struggle. Mechanical systems must be designed to handle thermal expansion and the corrosive atmosphere. Seals fail, Metals oxidize and corrode, glass softens. Anything organic would be destroyed almost instantly. Water, the universal solvent and building block of life as we know it, cannot exist in liquid form on Venus's surface. The high temperature ensures any water would instantly boil, but the lack of water in the atmosphere means there's essentially no humidity. Surface humidity is less than 0.1%. Any water brought to the surface would flash to steam, dissociate in the atmosphere, and eventually be broken down by solar ultraviolet radiation in the upper atmosphere. The hydrogen escapes to space, while the oxygen combines with other elements in the atmosphere. Perhaps the most fascinating and terrifying aspect of Venus is that it wasn't always this way. Scientists believe Venus may have once had liquid water oceans, similar to early Earth. For perhaps the first 2 billion years of its existence, Venus might have been habitable, with temperatures cool enough for liquid water to exist on the surface. But something went wrong. The greenhouse effect began to run away. Several factors may have contributed to this transformation. Venus receives about twice as much solar energy as Earth because it's closer to the Sun. This extra energy drove more water into the atmosphere through evaporation. Water vapor is itself a greenhouse gas, so this created a positive feedback loop. More water vapor led to more warming, which led to more evaporation, which led to more warming. Eventually, the oceans evaporated completely. The water vapor was broken apart by solar ultraviolet radiation, the hydrogen escaped to space, and Venus became the hellish desert world we see today. The lack of a strong magnetic field contributed to this loss. Unlike Earth, which has a powerful magnetic field generated by its liquid iron core, Venus has at most a weak-induced magnetic field. This left the atmosphere more vulnerable to the solar wind, which could strip away atmospheric molecules, including the hydrogen from water molecules. Over billions of years, Venus lost most of its original water to space. The dense carbon dioxide atmosphere remained because carbon dioxide is heavier and more difficult for solar wind to strip away. Volcanic outgassing continuously added more carbon dioxide, while the lack of liquid water meant no carbon cycle like Earth's to remove carbon dioxide from the atmosphere. On Earth, carbon dioxide dissolves in rainwater, reacts with rocks to form carbonates, and is eventually subducted into the mantle through plate tectonics, keeping atmospheric levels relatively low. Venus lacks this cycle, so carbon dioxide accumulated relentlessly. Living on Venus's surface is essentially impossible with current or near-future technology. You would need a pressure vessel capable of withstanding 93 atmospheres of pressure, cooling systems that could operate in 867-degree heat, and protection against the corrosive atmospheric chemistry. Power generation would be problematic since traditional solar panels can't withstand the heat and are useless beneath the clouds anyway. Nuclear power might work, but dissipating waste heat in such a hot environment would be challenging. However, about 30 to 40 miles up in Venus's atmosphere, conditions become surprisingly Earth-like. At this altitude, the pressure drops to about 1 atmosphere, the temperature hovers around 70 degrees Fahrenheit, and there's actually more sunlight than reaches Earth's surface since you're above the clouds. This region has sparked proposals for floating habitats or colonies, essentially airships that drift through Venus's upper atmosphere, suspended by breathable air which is buoyant in Venus's carbon dioxide atmosphere. These hypothetical cloud cities would face their own challenges. They'd need to be airtight since the outside atmosphere is still carbon dioxide with sulfuric acid clouds. Solar radiation above the clouds is intense. The acid rain would corrode external surfaces. The super-rotating winds would carry the habitats around the planet every 4 days, creating a situation where the sun never sets, but instead circles endlessly around the horizon. Still, of all the environments in the solar system beyond Earth, Venus's upper atmosphere might be one of the more accessible, offering relatively benign conditions just a few dozen miles above one of the most hostile surfaces imaginable. But we're discussing living on the planets, not floating above them, and Venus's surface remains a place where human presence is limited to brief visits by robotic emissaries, sacrificial probes designed to survive just long enough to send back a few measurements before the environment consumes them. It's a world that simultaneously fascinates and repels us, a mirror of what Earth might become if our own greenhouse effect runs away. A cautionary tale written in sulfuric acid and supercritical carbon dioxide. Continuing our journey outward, we arrive at Mars, the red planet, humanity's favourite destination for dreams of colonisation. Unlike Mercury and Venus, Mars actually seems plausible as a place where humans might one day live, work, and possibly even thrive. But don't let the comparatively benign reputation fool you. Mars is still an extraordinarily hostile environment that presents challenges far beyond anything humans have encountered on Earth. Mars is smaller than Earth, about half the diameter and 1/10 the mass. This smaller size has profound implications. The lower mass means weaker gravity, just 38% of Earth's surface gravity, the same as Mercury. It also means Mars cooled faster after its formation, likely shutting down its magnetic field billions of years ago. Without a magnetic field, the solar wind has been slowly stripping away Mars's atmosphere for eons, thinning it to a whisper of what it once was. Today, Mars's atmosphere is incredibly thin, with a surface pressure averaging just 600 pascals, less than 1% of Earth's atmospheric pressure. This is roughly equivalent to the pressure at an altitude of 22 miles above Earth's surface, well into the stratosphere. At this pressure, water cannot exist in liquid form. If you placed a glass of water on Mars's surface, it would simultaneously boil and freeze, first bubbling as the water vapour escapes, then freezing solid as evaporative cooling drops the temperature below freezing. The atmosphere that does exist is 95% carbon dioxide, with small amounts of nitrogen and argon. The thin atmosphere provides almost no greenhouse effect, so Mars is cold, very cold. Average temperatures hover around -80 degrees Fahrenheit, though temperatures vary widely. Near the equator on a summer afternoon, temperatures can climb to a relatively balmy 70 degrees Fahrenheit, but drop to -100 degrees Fahrenheit or colder at night. At the poles during winter, temperatures plunge to -220 degrees Fahrenheit, cold enough to freeze carbon dioxide solid. This temperature range creates dramatic seasonal effects. During the Martian winter, about 1/4 of the atmosphere freezes out at the poles, forming seasonal caps of carbon dioxide ice on top of the permanent water ice caps. This causes the atmospheric pressure across the entire planet to drop by 25 to 30%. In spring, the carbon dioxide sublimes back into gas, returning to the atmosphere, and the pressure rises again. It's a planet-wide breathing cycle, unique in the solar system. The thin atmosphere also means poor protection from radiation. On Earth, we're shielded by a thick atmosphere and a strong magnetic field. On Mars, you're exposed to the full brunt of cosmic rays, solar radiation, and solar particle events. The radiation dose on Mars's surface is about 40 times higher than on Earth. Over a year, a person on Mars would receive a dose of about 250 millisieverts, compared to the 2 to 3 millisieverts we receive on Earth from natural background radiation. This is enough to measurably increase cancer risk and potentially cause other health problems. Solar particle events pose an acute danger. During particularly violent solar storms, the Sun ejects massive amounts of charged particles. On Earth, these particles are deflected by our magnetic field or absorbed by the atmosphere, creating beautiful auroras at the poles. On Mars, they slam directly into the surface with little attenuation. A major solar particle event could deliver a lethal dose of radiation in hours. Any Martian habitat would need a storm shelter, an area with extra shielding where colonists could retreat during solar storms. The Martian landscape is simultaneously familiar and alien. The reddish colour comes from iron oxide, rust, coating much of the surface. Dust is everywhere, fine particles about 3 micrometers in diameter on average, suspended in the thin atmosphere and coating every surface. This dust is a major concern for any long-term presence on Mars. It's electrostatically charged, so it clings to everything: spacesuits, solar panels, equipment. It's also potentially toxic, containing perchlorates, oxidizing chemicals that could damage human health if inhaled or ingested. Dust storms are common on Mars, ranging from local dust devils that spiral across the landscape to regional storms covering large swathes of a hemisphere, to rare global dust storms that can enshroud the entire planet for months. During a global dust storm, sunlight reaching the surface can be reduced by 99%, creating twilight conditions even at noon. Solar panels become essentially useless. Temperatures drop because dust in the atmosphere blocks sunlight while also preventing heat from escaping at night. The dust eventually settles, but global dust storms can last 3 to 4 months, posing serious challenges for solar-powered equipment and habitats. Mars does have water, frozen as ice beneath the surface and mixed with the permanent polar caps. Radar observations have revealed extensive subsurface ice deposits, particularly at higher latitudes. Near the poles, ice can be found just inches beneath the surface. These ice deposits represent a crucial resource for future Mars missions, providing water for drinking, growing food, and producing oxygen and hydrogen for life support and rocket fuel. The Martian day, called a sol, is conveniently close to Earth's, lasting 24 hours and 39 minutes. This similarity would help preserve human circadian rhythms, making long-term habitation psychologically easier than on worlds with radically different day lengths. The year is about 687 Earth days, nearly twice as long as Earth's, so seasons last roughly twice as long. Mars also has a significant axial tilt of 25 degrees, similar to Earth's 23.5 degrees, so it experiences seasons in a way that would feel familiar. The landscape of Mars is spectacular and varied. The planet hosts the largest volcano in the solar system, Olympus Mons, a shield volcano 16 miles high and 374 miles across at its base. It towers 3 times higher than Mount Everest. The Valles Marineris, a vast canyon system, stretches more than 2,500 miles across Mars's surface, with depths reaching 4 miles. For comparison, this makes the Grand Canyon look like a modest crack in the ground. Ancient river valleys and lake beds show that water once flowed on Mars's surface, though how long ago and for how long remains debated. Some features suggest Mars may have had an ocean covering much of its northern hemisphere billions of years ago. Building a habitat on Mars presents challenges but not insurmountable ones. You'd need a pressure vessel to contain breathable air against the near vacuum outside. Thick walls or berms of Martian soil could provide radiation shielding, with estimates suggesting about 16 feet of soil or rock would reduce radiation to acceptable levels. Greenhouses could grow food using Martian soil as a base, though you'd need to remove the perchlorates and add organic matter and nutrients. Solar panels would work, though they'd need frequent cleaning to remove dust, or you could use nuclear power, which would be more reliable, especially during dust storms or the long Martian winter. Water extraction would be crucial. Heating subsurface ice to melt it, then condensing the vapour, would provide water. Electrolysis could split water into hydrogen and oxygen. The atmosphere, despite being thin, is mostly carbon dioxide, which could be converted into useful products. The Sabatier reaction combines carbon dioxide with hydrogen to produce methane and water, and the methane could be used as rocket fuel. This in situ resource utilisation would be essential for any self-sustaining Mars colony. The lower gravity poses interesting challenges. While the 38% gravity makes moving heavy equipment easier and reduces strain on structures, prolonged exposure to low gravity can have serious health effects. Astronauts on the International Station in microgravity experience bone density loss, muscle atrophy, vision changes, and cardiovascular deconditioning. Mars's gravity might be enough to mitigate these effects, or it might not. We simply don't know because no human has spent extended time in partial gravity. There are concerns that children born and raised in Mars's gravity might never be able to visit Earth, as their bones and muscles might not develop strongly enough to support Earth's gravity. The psychological challenges of Mars colonization would be substantial. Mars is far from Earth, typically taking 6 to 9 months to reach with current propulsion technology. Communication with Earth would have a time delay ranging from 4 to 24 minutes each way, depending on the relative positions of the planets, making real-time conversation impossible. Colonists would feel isolated, cut off from the rest of humanity, in a way no human has experienced before. The landscape, while varied, is uniformly red and brown, lacking the greens and blues that dominate Earth's vistas. The thin atmosphere means no blue sky, just a butterscotch haze during the day fading to dark at twilight. But unlike Mercury and Venus, Mars seems potentially habitable with sufficient technology. We could build habitats there. We could grow food. With enough infrastructure, humans could survive and perhaps even flourish. Mars is cold, dry, hostile and dangerous, but it's not immediately lethal. You could, in theory, walk out of your habitat in just a spacesuit, rather than needing the enormous pressure vessels required for Venus or the extreme thermal protection necessary for Mercury. Mars is hard, but it's the right kind of hard, challenging rather than impossible. The presence of water ice, the availability of carbon dioxide for chemical processes, the moderate day length, the interesting and varied terrain, all make Mars the most attractive target for human colonization beyond Earth. It's our celestial neighbour, close enough to reach but different enough to be fascinating, harsh enough to be challenging but not so hostile as to be completely prohibitive. Of all the planets in our solar system, Mars is the one where humans might actually build a second home. Moving beyond the rocky inner planets, we enter a realm of giants, worlds so large that they dwarf Earth and everything we've discussed so far. First among these titans is Jupiter, the king of planets, massive beyond comprehension. Jupiter contains more than twice the mass of all other planets, moons and asteroids in the solar system combined. It's so large that 300 Earths could fit inside its volume. But Jupiter presents an immediate and fundamental problem. There's no surface to stand on. Jupiter is a gas giant, a world composed primarily of hydrogen and helium, with no solid surface in the traditional sense. The planet transitions gradually from gas to liquid to perhaps a solid core, but there's no clear boundary where you could say, this is the surface. So when we talk about living on Jupiter, we need to redefine what that means. Instead of standing on solid ground, we're talking about descending through increasingly dense layers of atmosphere, experiencing crushing pressures and rising temperatures until your vessel or body can't withstand the conditions any longer. Let's imagine descending into Jupiter's atmosphere in a hypothetical spacecraft designed to survive the journey as long as possible. We begin in space above Jupiter's cloud tops. The temperature here is frigid, about negative 230 degrees Fahrenheit. The pressure is essentially zero, comparable to the vacuum of space. Jupiter's powerful magnetic field, the strongest of any planet, immediately makes its presence known. Radiation levels are intense, far higher than at Earth. Jupiter's magnetosphere traps charged particles from the solar wind, creating radiation belts similar to Earth's Van Allen belts, but vastly more powerful. As we descend into the uppermost atmosphere, we enter a region of haze and cloud layers. Jupiter's appearance from space shows bands of different colours, light zones and dark belts circling the planet. These bands represent different atmospheric regions with distinct chemistry and circulation patterns. The light-coloured zones are regions where gases are rising, carrying ammonia ice crystals aloft. The crystals form bright white clouds. The darker belts are regions where gases are descending, and the clouds are lower and redder, coloured by complex organic compounds created by chemical reactions in the atmosphere. At the point where the pressure reaches about 1 bar, equivalent to Earth's sea level pressure, the temperature has warmed to about negative 160 degrees Fahrenheit. Scientists conventionally define this as Jupiter's surface, even though there's nothing solid here. This is the region we see when we look at Jupiter through a telescope. The winds here are fierce, reaching speeds over 400 miles per hour, organised into jet streams that remain remarkably stable over centuries. Continuing our descent, we pass through the cloud layers. First is ammonia ice, forming at pressures around 0.5 to 0.8 bars. Below that, around 2 bars of pressure, is a cloud layer made of ammonium hydrosulfide, a compound that likely contributes to the colourful appearance of Jupiter's clouds. Deeper still, around 5 to 7 bars of pressure, water ice and liquid water droplets form clouds. The temperature and pressure continue to rise as we descend. After travelling about 45 miles down from the 1 bar level, we've reached a pressure of about 10 bars and a temperature near the freezing point of water. The atmosphere here is dense, thick with hydrogen and helium, and the pressure would be crushing to an unprotected human. An ordinary spacesuit would crumple like tin foil. You'd need a pressure vessel, a spherical hull of thick steel or advanced composites, to withstand the forces trying to compress you. At 150 miles depth, the pressure has increased to about 100 bars, and the temperature has climbed to around 800 degrees Fahrenheit. This is as deep as the Galileo atmospheric probe managed to penetrate in 1995 before being destroyed by the heat and pressure. By this point, we're essentially swimming through a hot, dense fluid rather than flying through a gas. The distinction between gas and liquid becomes blurred as the hydrogen approaches critical point conditions. Continuing deeper still, beyond where any spacecraft has gone, the pressure becomes truly immense. At several hundred miles deep, the pressure exceeds 1,000 bars, and the temperature surpasses 1,800 degrees Fahrenheit. The hydrogen, subjected to these extreme conditions, begins to behave very strangely. At pressures around 4,000 bars and temperatures around 18,000 degrees Fahrenheit, about 6,000 miles below the cloud tops, hydrogen undergoes a phase transition to metallic hydrogen. Metallic hydrogen is a bizarre state of matter where the pressure is so intense that electrons are stripped from hydrogen atoms, creating a liquid metal. This metallic hydrogen layer is thought to comprise the bulk of Jupiter's interior. It's electrically conductive, and the churning convective motion of this metallic layer is believed to generate Jupiter's powerful magnetic field through a dynamo effect, similar to how Earth's liquid iron core generates its magnetic field. Even deeper, perhaps 35,000 miles down, about halfway to Jupiter's centre, the pressure might reach millions of bars, and the temperature could exceed 36,000 degrees Fahrenheit. At these depths, we might encounter Jupiter's core if it exists as a discrete structure. Current models suggest Jupiter may have a core composed of rock, metal, and ices, water, ammonia, and methane compressed into exotic high-pressure phases, with a mass perhaps 10 to 20 times Earth's mass. However, recent data from the Juno mission suggests this core might be diffuse, mixed with the surrounding layers rather than existing as a distinct solid or liquid ball. So what would it be like to try to live in Jupiter's atmosphere? At the top layers, the cold and radiation would kill you quickly. Descending deeper, you'd enter regions where temperatures are briefly Earth-like, but the pressure would be crushing, and you're surrounded by an atmosphere of hydrogen and helium, unbreathable and offering no oxygen. Deeper still, temperatures soar, and pressures become so extreme that your vessel would be compressed like an aluminum can in a hydraulic press. Jupiter's Great Red Spot, the most famous storm in the solar system, deserves special mention. This is an anticyclonic storm, a high-pressure system large enough to swallow 3 Earths. It's been raging for at least 300 years, perhaps much longer, fed by heat rising from Jupiter's interior and the chaotic dynamics of the atmosphere. Wind speeds in the storm reach 270 to 425 miles per hour. The storm's colour, a reddish-brown hue, comes from complex organic molecules created by the interaction of sunlight with chemicals in the atmosphere. Diving into the Great Red Spot would subject you to violent turbulence, extreme winds, and lightning bolts far more powerful than any on Earth. Jupiter also has lightning, detected by multiple spacecraft and even observed from Earth when strikes occur on Jupiter's night side. Some lightning bolts are estimated to be 3 times more energetic than Earth's largest lightning strikes. These titanic electrical discharges would threaten any spacecraft or structure with electromagnetic pulses and direct strikes. The radiation belt surrounding Jupiter would fry electronics and kill any human not shielded by significant amounts of lead or other dense materials. The radiation is intense enough that spacecraft visiting Jupiter must be specially hardened to survive. Europa, one of Jupiter's moons, receives such intense radiation that its icy surface is constantly bombarded, creating a harsh environment despite the moon's potential subsurface ocean. But could anything live in Jupiter's atmosphere? Science fiction has long explored this idea. Carl Sagan and others speculated about hypothetical Jovian life forms, floaters that drift in the atmosphere, eating organic molecules created by lightning, hunters that swim through the dense layers preying on floaters, sinkers that lose buoyancy and fall into the hot depths where they're destroyed. While this remains pure speculation, Jupiter's atmosphere does contain the raw ingredients for organic chemistry: hydrogen, carbon, nitrogen, oxygen. Lightning and ultraviolet radiation drive chemical reactions, creating complex molecules. Water exists as ice and liquid in the cloud layers. Some regions of the atmosphere have Earth-like temperatures and pressures, at least briefly as you pass through, but the challenges are formidable. There's no solid surface to anchor to, no easy access to minerals and elements needed for complex biochemistry, constant vertical currents that would carry organisms between regions of vastly different temperatures and pressures. Any life in Jupiter's atmosphere would need to maintain buoyancy, floating in a narrow band of tolerable conditions while avoiding being carried into the lethal depths below or the frozen, radiated heights above. For human habitation, Jupiter offers nothing but death in various forms. You can't land on a gas giant. You can't mine it for resources easily. You can't breathe its atmosphere or drink its water. The radiation, pressure, temperature extremes and sheer violence of the environment rule out any direct human presence. Jupiter is a place we can visit with robots, observe from orbit and study from afar, but it will never be a home for humanity. It's too alien, too extreme, too fundamentally different from the terrestrial worlds we evolved on. Jupiter's moons, however, are another story. Europa, Ganymede and Callisto all have potential for human outposts or bases, but Jupiter itself, it's a giant laboratory, a physics experiment playing out on a planetary scale, a reminder that our solar system contains worlds utterly unlike our own, places where the rules seem different and the very concept of surface loses meaning. Beyond Jupiter lies Saturn, the second largest planet in our solar system, and perhaps the most beautiful. Saturn's magnificent ring system, visible even through small telescopes, has captivated observers for centuries. When Galileo first observed Saturn through his primitive telescope in 1610, he couldn't make out the rings clearly and thought the planet had ears or companion objects. Later, as telescopes improved, astronomers realized they were seeing an extraordinary ring system, unlike anything else in the solar system. But beauty doesn't mean benign. Like Jupiter, Saturn is a gas giant with no solid surface, and descending into Saturn's atmosphere would be similar to descending into Jupiter's, though with some interesting differences. Saturn is less dense than Jupiter. In fact, Saturn's average density is less than water, meaning that if you could find an ocean large enough, Saturn would float. This lower density reflects Saturn's composition, mostly hydrogen and helium, with proportionally less of the heavier elements compared to Jupiter. The view from space shows Saturn as a pale yellow planet, less colourful than Jupiter. Saturn's atmosphere has bands and zones like Jupiter's, but they're more subdued, less distinct. The entire planet appears hazier, with a thick layer of ammonia ice crystals creating a uniform haze that mutes the underlying colours and features. Occasionally, massive white storms erupt, particularly in Saturn's northern hemisphere during the planet's summer. These storms can grow to encircle the entire planet, creating temporary bright features that rival Saturn's normally uniform appearance. Saturn's cloud tops are colder than Jupiter's, with temperatures around -220 degrees Fahrenheit at the 1 bar pressure level. This makes Saturn the coldest of the gas giants, even though it radiates about 2.5 times more energy than it receives from the Sun. Like Jupiter, Saturn has an internal heat source, energy left over from the planet's formation supplemented by helium rain in the interior. Helium, being heavier than hydrogen, slowly separates and sinks towards Saturn's core, releasing gravitational potential energy as heat through this process. The winds on Saturn are the fastest in the solar system. At the equator, jet streams reach velocities of 1 to 100 miles per hour, far faster than Jupiter's winds and faster than the speed of sound in Saturn's atmosphere at those altitudes. These supersonic winds create shock waves and turbulence, though the thick atmosphere dampens the violence somewhat. The wind patterns are organised into multiple jet streams at different latitudes, creating a pattern of eastward and westward flows that shape the cloud bands. Descending into Saturn's atmosphere, we'd follow a similar profile to Jupiter. Cloud layers of ammonia ice, then ammonium hydrosulfide, then water clouds, arranged at different altitudes based on where each compound condenses. The temperature and pressure rise as we descend. Lightning has been detected in Saturn's atmosphere, particularly in the water cloud layer, with some strikes being even more powerful than Jupiter's lightning, creating radio emissions detectable from Earth. About 6,000 miles down, at pressures around 4,000 bars and temperatures around 18,000 degrees Fahrenheit, hydrogen transitions to metallic hydrogen, just as in Jupiter. However, because Saturn is smaller and less massive than Jupiter, the metallic hydrogen layer is proportionally smaller. The transition occurs deeper into the planet, and the region of metallic hydrogen extends for about 12,000 miles, rather than Jupiter's 30,000 miles or more. Saturn likely has a core of rock, ice, and metal similar to Jupiter's, with a mass estimated at about 10 to 20 Earth masses. Recent data suggests this core might also be diffuse or partially dissolved, mixed with the overlying layers. The exact structure of Saturn's interior remains uncertain, as we can only infer it from measurements of the planet's gravitational field, magnetic field, and energy output. Saturn's magnetic field is peculiar. It's much weaker than Jupiter's and almost perfectly aligned with the planet's rotation axis, within 1 degree. This perfect alignment is puzzling because dynamo theory suggests the magnetic field should be tilted relative to the rotation axis, due to turbulence in the metallic hydrogen layer. Various explanations have been proposed, including unusual structures in Saturn's interior or a stable dynamo configuration, but the mystery remains unsolved. The rings, Saturn's most famous feature, don't affect the planet's atmosphere directly, but they create a unique radiation environment. Particles from the rings, knocked loose by micrometeoroids or charged particle impacts, can enter Saturn's atmosphere, depositing water and other compounds. The rings also cast shadows on the planet, creating dark bands across Saturn's cloud tops near the equinoxes when the Sun illuminates the ring plane edge-on. Saturn's rings are made mostly of water ice, with chunks ranging from millimetre-sized particles to building-sized boulders. They're remarkably thin, only about 30 feet thick in most places despite stretching more than 175,000 miles from inner edge to outer edge. The rings are divided into several main sections, named alphabetically in order of discovery. The D ring closest to the planet, then C, B, A, F, G and E rings extending outward. The brightest and most massive rings are the B and A rings, visible from Earth in small telescopes. But none of this makes Saturn habitable. Like Jupiter, it's a gas giant without a surface, with crushing pressures, extreme temperatures and no breathable atmosphere. The ring plane would be particularly dangerous to traverse, filled with countless particles travelling at orbital velocities. A collision with even a small ice particle at these speeds would be catastrophic, like being hit by a bullet. The rings are beautiful from a distance, but deadly up close. Saturn's upper atmosphere does have regions where temperatures and pressures are theoretically compatible with human physiology for a brief span as you descend through them. But you're surrounded by hydrogen and helium, with no oxygen to breathe, intense radiation from Saturn's magnetosphere, and winds travelling at hundreds of miles per hour. Any structure or vessel would need to be impossibly robust to withstand the forces involved. The radiation environment around Saturn is less intense than Jupiter's, but still hazardous. Saturn's magnetic field traps charged particles, creating radiation belts, though these are weaker and less extensive than Jupiter's. Still, prolonged exposure would be harmful to humans and damaging to electronics. Any mission to Saturn's orbit requires radiation shielding. Could life exist in Saturn's atmosphere? The same speculations that apply to Jupiter apply here, perhaps even more so. Saturn's atmosphere contains organic molecules, products of photochemistry in the upper atmosphere. The Cassini spacecraft detected complex hydrocarbons, the building blocks of life. Water clouds exist deep in the atmosphere. Lightning provides energy. But the lack of a surface, the difficulty of concentrating nutrients, and the extreme vertical temperature gradients make life in Saturn's atmosphere seem unlikely. Saturn's moons, particularly Titan and Enceladus, are far more interesting for astrobiology and potential human exploration. Titan has a thick atmosphere and liquid methane lakes on its surface. Enceladus has geysers erupting from a subsurface ocean. These moons offer more possibilities than Saturn itself. But Saturn, the planet proper, is another gas giant that humans will observe, study and admire from a distance, but never truly inhabit. It's a world of beauty and violence, where winds scream at supersonic speeds, through clouds of ammonia ice, where helium rain falls through metallic hydrogen seas, where the pressure and temperature at the core might approach those at the centre of a star, though without enough mass to ignite fusion. Venturing even farther from the Sun, we reach Uranus, the seventh planet and the first of the ice giants. Uranus is a world of strange tilts and frigid mysteries, fundamentally different from the gas giants we've explored. At nearly 2 billion miles from Earth, Uranus is so distant that it appears as little more than a pale blue-green dot, even in powerful telescopes. The first thing to understand about Uranus is its bizarre tilt. Most planets rotate with their poles roughly perpendicular to their orbital plane, like spinning tops tilted slightly. But Uranus rotates on its side with an axial tilt of 98 degrees. This means Uranus essentially rolls around the Sun like a ball rolling down a hill. The poles alternately point almost directly at the Sun, creating seasons unlike anything in the solar system. During a Uranian summer, one pole experiences continuous sunlight for 42 Earth years, while the other pole remains in continuous darkness. Then the situation reverses for another 42 years. This extreme tilt likely resulted from a massive collision early in Uranus's history, when a large body struck the planet with enough force to knock it on its side. This same impact may have also scrambled Uranus's interior, mixing the layers and potentially affecting the planet's magnetic field and internal structure. The impact might also explain why Uranus radiates so little heat. Unlike Jupiter, Saturn and Neptune, which all radiate more than twice as much energy as they receive from the Sun, Uranus radiates only about 1.1 times the energy it receives, barely any excess heat at all. Something in Uranus's interior prevents heat from escaping efficiently, though what that might be remains unclear. The atmosphere of Uranus is composed primarily of hydrogen and helium, like Jupiter and Saturn, but with a much higher proportion of ices, water, ammonia and methane in compressed exotic forms. These ices make up the bulk of Uranus's mass and define it as an ice giant rather than a gas giant. The term ice is misleading because these materials aren't frozen solid. Instead, they exist as hot, dense fluids under extreme pressure deep in the planet's interior. The visible atmosphere of Uranus is remarkably bland compared to Jupiter and Saturn. The cloud tops appear almost featureless, a uniform pale cyan colour with little structure. This colour comes from methane in the upper atmosphere, which absorbs red light and reflects blue and green light, giving Uranus its distinctive hue. The clouds are composed of methane ice crystals, forming at a temperature of about negative 320 degrees Fahrenheit and a pressure around 1.5 bars. The lack of visible features reflects Uranus's weak internal heat source. With little heat rising from below, the atmosphere remains stable and stagnant. There's minimal convection to drive weather patterns, and the clouds remain uniform and undisturbed. Occasionally, astronomers detect bright spots or small storms in Uranus's atmosphere, but these are rare events rather than constant features. The atmosphere is layered and hazy with multiple cloud decks at different altitudes, but from outside, it all blends into a uniform appearance. The temperature at the cloud tops averages around negative 320 degrees Fahrenheit, making Uranus the coldest planet in the solar system, despite being closer to the Sun than Neptune. The upper atmosphere is frigid and thin, with pressures and temperatures that would freeze anything solid and crack materials through thermal stress. Descending deeper, the temperature and pressure rise gradually. At the 1 bar level, the temperature is around negative 350 degrees Fahrenheit. Deeper still, following the adiabatic temperature gradient, conditions become increasingly extreme. Below the visible clouds, perhaps a few hundred miles down, the atmosphere transitions into a mantle of water, ammonia, and methane ices, mixed with hydrogen and helium. This isn't a sharp boundary, but a gradual transition as the density and pressure increase. These ices exist in supercritical fluid states, acting like both liquid and gas simultaneously. The temperature in this region might reach several thousand degrees Fahrenheit, and the pressure climbs to millions of bars. About 5,000 miles down, we might reach Uranus's core, a region of compressed rock and metal, perhaps similar to Earth in composition but under unimaginable pressures and temperatures. The core might have a mass of about half an Earth mass to several Earth masses, but its exact size and composition remain uncertain. We've never sent a probe into Uranus's atmosphere, and our knowledge comes entirely from remote observations and theoretical models. Uranus's magnetic field is one of its strangest features. Unlike the magnetic fields of Earth, Jupiter, or Saturn, which are roughly aligned with the rotation axis and centered on the planet, Uranus's magnetic field is tilted 59 degrees from the rotation axis and offset from the center by about 1/3 of the planet's radius. This creates a wildly asymmetric magnetosphere that wobbles and flips as Uranus rotates. The magnetic field lines on one side of the planet point outward, while on the other side they point inward, creating a twisted, complex structure unlike any other planetary magnetosphere. This bizarre magnetic field configuration suggests something unusual in Uranus's interior. The dynamo generating the field might be located in a thin shell of conducting fluid relatively close to the surface, rather than deep in the core like Earth's dynamo. The high-pressure ices, under the right conditions of temperature and pressure, can become electrically conductive, and it's in these layers that Uranus's magnetic field is probably generated. The winds on Uranus blow primarily from west to east, retrograde relative to the planet's rotation. Wind speeds reach up to 560 miles per hour at some latitudes. Given the planet's weak internal heat and the extreme seasonal variations, you might expect asymmetric wind patterns with strong differences between the summer and winter hemispheres. Surprisingly, observations show that the winds are relatively symmetric and don't vary much between the lit and dark hemispheres. This suggests the atmosphere has enormous thermal inertia, with the vast mass of air storing and redistributing heat so effectively that the seasons have little immediate impact on wind patterns. Living on or in Uranus is as impossible as on Jupiter or Saturn, only colder and more alien. There's no surface, only a gradual descent through increasingly dense and hot layers until you're crushed and cooked. The cold at the cloud tops would freeze anything solid. The radiation from Uranus's magnetosphere, while weaker than Jupiter's or Saturn's, would still be hazardous. The complete lack of sunlight on the winter side of the planet, lasting for decades, would require artificial lighting and power sources. The atmosphere is unbreathable, mostly hydrogen and helium with methane and other volatiles. There's no oxygen, no water in accessible form, no organic compounds to speak of. The constant darkness on one hemisphere and perpetual twilight on the other during most seasons would be psychologically devastating. The cyan-green sky, the result of methane absorption, would be eerie and alien, lacking the familiar colours of Earth's atmosphere. Uranus's moons are also ice-covered worlds, frozen solid at temperatures around negative 370 degrees Fahrenheit. They have cratered surfaces and some geological features, but they're small, cold, and distant. The largest, Titania, is only half the diameter of Earth's moon. These moons don't offer much more hope for human habitation than Uranus itself. Uranus represents a class of planet common in the galaxy, but completely alien to human experience. It's a world where the seasons last decades, where the magnetic field tumbles through space as the planet rotates, where methane clouds float in a pale blue sky, and where the interior is an ocean of compressed ices at temperatures and pressures beyond anything we can recreate on Earth. It's a reminder that the variety of worlds in the universe is limited only by the laws of physics and chemistry, and those laws permit extremes far beyond our everyday experience. At the outer edge of the planetary system, nearly 3 billion miles from the Sun, lies Neptune, the eighth and final major planet. Neptune is Uranus's near twin in size and composition, another ice giant with a similar internal structure and atmospheric composition. But where Uranus is bland and featureless, Neptune is dynamic and stormy, with active weather patterns visible even from Earth orbit telescopes. Neptune appears as a beautiful deep blue sphere coloured by methane in its atmosphere, just like Uranus, but with a richer, more saturated hue. The colour is striking, reminiscent of a tropical ocean, though the temperatures here are anything but tropical. The cloud tops average around negative 330 degrees Fahrenheit, among the coldest in the solar system. At this distance from the Sun, sunlight is dim, about 1,000 times fainter than on Earth. Neptune receives so little solar energy that it seems impossible for it to generate the vigorous weather observed. Yet Neptune has the most active atmosphere of any of the outer planets. The explanation lies in Neptune's internal heat. Unlike Uranus, Neptune radiates about 2.6 times more energy than it receives from the Sun, powered by some internal heat source. The mechanism generating this heat remains uncertain. It could be primordial heat left over from the planet's formation, or heat from radioactive decay in the core, or possibly gravitational contraction as the planet slowly shrinks over billions of years. Whatever the source, this internal heat drives powerful convection currents in Neptune's atmosphere, creating the dynamic weather patterns we observe. Neptune's atmosphere is dominated by ferocious winds, the fastest sustained winds in the solar system. Near the equator, jet streams reach velocities of 1,300 miles per hour, and in some regions winds scream at up to 1,500 miles per hour, approaching twice the speed of sound in Neptune's atmosphere. These supersonic winds create zones of intense turbulence, with storms and vortices forming and dissipating on timescales of months to years. The most famous feature on Neptune was the Great Dark Spot discovered by Voyager 2 in 1989. This was an Earth-sized anticyclonic storm similar to Jupiter's Great Red Spot, visible as a dark oval near Neptune's equator. The storm was accompanied by bright white clouds, probably methane ice crystals forming at high altitudes. By the time the Hubble Space Telescope observed Neptune in 1994, the Great Dark Spot had vanished, likely dissipated or moved to a different latitude. Other dark spots have appeared since, showing that these storms are transient features rather than permanent fixtures like Jupiter's Great Red Spot. Bright wispy clouds appear at high altitudes on Neptune made of methane ice crystals. These clouds cast shadows on the lower cloud layers, allowing astronomers to measure their altitude, typically about 30 to 50 miles above the main methane cloud deck. The presence of these high-altitude clouds indicates strong vertical motion, with air currents carrying methane vapor to great heights, where it freezes and forms cirrus-like clouds. Neptune's atmospheric structure includes multiple cloud layers. The uppermost clouds are methane ice at a pressure of about 1.5 bars and a temperature of around 120 Kelvin. Below this, perhaps at 3 to 4 bars of pressure, is a cloud layer possibly made of hydrogen sulfide ice. Deeper still are water and ammonia clouds, though these are never directly visible from outside because they're hidden beneath the higher layers. Descending into Neptune's atmosphere would follow the now familiar pattern, increasing pressure and temperature as you go deeper. The hydrogen and helium atmosphere gradually transitions into a mantle of water, ammonia, and methane ices in supercritical fluid states. The pressure and temperature in this region might reach millions of bars and tens of thousands of degrees. At the centre, Neptune probably has a rocky core of silicates and metals, perhaps 1 to 2 Earth masses, but the exact structure remains speculative. Neptune's magnetic field, like Uranus's, is tilted and offset from the centre, though not as extremely. The magnetic axis is tilted 47 degrees from the rotation axis and offset by about 55% of the planet's radius. This creates an asymmetric magnetosphere that rotates with the planet, presenting different faces to the solar wind as Neptune spins. The similarity between Neptune's and Uranus's magnetic fields suggests they share a common generation mechanism, probably dynamos operating in a shell of conducting ices at intermediate depths. The environment around Neptune is hostile in every way. The extreme cold would freeze any exposed surface instantly. The winds would tear apart any structure not anchored and reinforced. The darkness, with sunlight 900 times dimmer than Earth, would make solar power impractical. The distance from the Sun means communication with Earth would have a round-trip light time of over 8 hours, making real-time control impossible. Neptune's largest moon, Triton, is a fascinating world in its own right. Triton is the only large moon in the solar system with a retrograde orbit, meaning it orbits Neptune backward compared to the planet's rotation. This strongly suggests Triton was captured by Neptune's gravity rather than forming in place. Triton has a thin nitrogen atmosphere and geysers of nitrogen gas erupting from its surface, driven by solar heating of subsurface nitrogen ice. The surface temperature is around -390 degrees Fahrenheit, making Triton one of the coldest objects in the solar system. But Triton's fate is sealed. Its retrograde orbit is slowly decaying due to tidal interactions with Neptune. In about 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces will tear it apart, creating a spectacular ring system around Neptune, perhaps rivaling or exceeding Saturn's rings in size and brightness. But that's far in the future. For now, Triton remains a frozen, active world, and possibly the most interesting object in the Neptune system. Living on Neptune itself is impossible. Like all the giant planets, it offers no surface, only a descent through increasingly hostile conditions until you're destroyed by pressure, temperature, or both. The beauty of Neptune's deep blue colour and dynamic cloud patterns can only be appreciated from a distance. Up close, Neptune is a world of darkness, cold, and violence, a planet of methane ice clouds and supersonic winds where storms the size of Earth appear and vanish on a whim, where the atmosphere never stops moving and the interior radiates heat from some unknown source. Neptune marks the boundary of the major planets, the edge of the realm we've known since ancient times. Beyond Neptune lie smaller worlds, dwarf planets, and icy bodies that comprise the Kuiper Belt and scattered disk. But Neptune itself is the last of the giants, the final sentinel standing guard at the edge of the planetary system, a beautiful, deadly world that embodies all the violence and wonder of the outer solar system. Beyond Neptune's orbit lies a vast realm of frozen worlds, the domain of dwarf planets, comets, and countless icy bodies too small to be called planets, but too numerous and significant to ignore. This is the Kuiper Belt and Scattered Disk region, extending from about 30 astronomical units from the Sun out to perhaps 100 astronomical units or more. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles, so we're talking about regions 3 billion to 9 billion miles from the Sun. The most famous resident of this region is Pluto, once considered the 9th planet but reclassified as a dwarf planet in 2006. This reclassification sparked controversy and debate, but it reflected our growing understanding of the outer solar system. Pluto isn't alone out there. It shares its region with thousands of similar objects, many comparable in size to Pluto itself. Eris, another dwarf planet, is actually more massive than Pluto, though slightly smaller in diameter. Other named dwarf planets include Makemake, Haumea, and Ceres, the largest asteroid, located in the asteroid belt between Mars and Jupiter. Pluto itself is a fascinating world. The New Horizons spacecraft flew past Pluto in July 2015, providing our only close-up views of this distant world. The images revealed a complex geologically active surface, far more interesting than anyone expected. Pluto has mountains of water ice reaching up to 11,000 feet high, vast plains of frozen nitrogen called Sputnik Planitia, and possible cryovolcanoes that erupt ice and liquid water instead of molten rock. The temperature on Pluto averages around negative 380 degrees Fahrenheit, cold enough that most gases freeze solid. Nitrogen, carbon monoxide, and methane, which are gases on Earth, exist as ices on Pluto. These ices slowly sublimate in sunlight, creating a tenuous atmosphere that extends hundreds of miles above the surface. The atmospheric pressure is incredibly low, about 100,000 times less than Earth's, barely distinguishable from a vacuum. But Pluto's atmosphere is dynamic, as Pluto follows its highly elliptical orbit, coming as close as 30 astronomical units from the Sun at perihelion and moving out to 49 astronomical units at aphelion, and the surface temperature varies significantly. When Pluto is closer to the Sun, more ice sublimes and the atmosphere thickens. When Pluto moves farther away, the atmosphere freezes out and falls back to the surface as snow. It's a world where the atmosphere itself precipitates, creating snowfalls of nitrogen and methane that coat the surface in fresh frost. Living on Pluto would present challenges unlike any we've encountered so far. The cold is beyond extreme, far colder than any terrestrial environment. At negative 380 degrees Fahrenheit, any exposed water would freeze instantly, as would oxygen and nitrogen. Carbon dioxide, which sublimes at negative 109 degrees Fahrenheit at Earth's pressure, is solid and stable on Pluto. Even materials we think of as permanent and unchanging, like rubber or plastics, would become brittle and shatter at these temperatures. The darkness is nearly total. Sunlight at Pluto is about 1,600 times dimmer than on Earth, roughly equivalent to twilight conditions. The Sun appears as just a bright star in the sky, no longer a disk but a point source, brighter than any other star but not the familiar warm presence we know from Earth. Shadows would be soft and indistinct, and the landscape would exist in perpetual twilight, illuminated only by dim sunlight reflected off the surface. But there's also unexpected light. Pluto has no clouds to block the stars, and with no light pollution the night sky would be spectacular. The Milky Way would stretch across the sky in vivid detail, and thousands of stars would be visible. Pluto's largest moon, Charon, would hang in the sky, never rising or setting because Pluto and Charon are tidally locked to each other. Charon would appear about 8 times larger than the Moon appears from Earth, a significant presence in Pluto's sky. The gravity on Pluto is weak, just 6% of Earth's. Walking would be impossible in the traditional sense. You'd bounce with each step, and a vigorous jump could launch you hundreds of feet into the air. Dropping something would take several seconds before it hit the ground, falling in slow motion. This weak gravity is part of why Pluto lost its status as a planet. It hasn't cleared its orbit of other debris, failing one of the 3 criteria for planetary status. Pluto's surface is varied and complex. Some regions are ancient, heavily cratered, and unchanged for billions of years. Other regions, like Sputnik Planitia, are geologically young, with surfaces only a few million years old, indicating ongoing activity. The nitrogen ice in Sputnik Planitia slowly flows in convection cells, like a lava lamp, driven by heat from Pluto's interior and phase changes in the ice. Mountains of water ice, buoyant in the denser nitrogen ice, float across the plain like icebergs on an Arctic sea. Pluto may have a subsurface ocean of liquid water, kept liquid by heat from radioactive decay in the planet's rocky core and insulated by a thick shell of ice. If this ocean exists, it could be 60 to 120 miles deep, a vast reservoir of water beneath the frozen surface. The presence of ammonia in the ice, suggested by spectral observations, would lower the freezing point of water, making such an ocean more plausible. But accessing this ocean would be monumentally difficult. You'd need to drill through tens of miles of ice at temperatures hundreds of degrees below zero, all while maintaining a pressure seal to prevent your drill hole from freezing shut. The energy requirements would be enormous, and the engineering challenges nearly insurmountable with current technology. Other dwarf planets in the outer solar system share similar characteristics. Eris, slightly more distant and massive than Pluto, is covered in frozen methane and appears as a bright reflective world. Makemake has a reddish colour, possibly due to organic compounds called tholins, created by cosmic ray bombardment of methane ice. Haumea is rapidly rotating and elongated, possibly the result of a massive collision that created a family of smaller objects in similar orbits. These worlds are the leftovers from the formation of the solar system, primitive bodies that never accreted into planets. They've remained largely unchanged for 4.6 billion years, frozen in the deep cold of the outer solar system. Studying them gives us insights into the early solar system's composition and the processes that formed the planets. Living on any of these distant worlds would require technology far beyond what we currently possess. The cold alone is a showstopper. Keeping anything warm enough to function would require enormous amounts of energy. Solar power is essentially useless at these distances, so you'd need nuclear power, either fission reactors or radioisotope thermoelectric generators. But even nuclear power has limits, and maintaining habitable temperatures in such extreme cold would be a constant battle. The distance from Earth is another huge challenge. Communication would have a round-trip light time of many hours, up to 11 hours for Pluto at its farthest. This makes real-time control impossible, and requires any missions or settlements to be highly autonomous. If something goes wrong, Earth can't help in any meaningful way. You're on your own, billions of miles from home with no possibility of rescue. The psychological isolation would be profound. Earth would appear as a pale blue dot next to the Sun, barely distinguishable from other bright stars. You'd be farther from Earth than any human has ever been, beyond the reach of immediate communication, living on a frozen ball of ice and rock at the edge of the solar system. The darkness, the cold, the isolation, all would weigh heavily on the human mind. Yet there's a certain poetry to these distant worlds. They're the edge of our solar system, the final outposts before interstellar space. Beyond them lies the heliopause, where the sun's solar wind gives way to the interstellar medium. The Voyager spacecraft have crossed this boundary and entered interstellar space, but they're still gravitationally bound to the sun, still part of the solar system in the broadest sense. These dwarf planets and icy bodies will probably never host human colonies. They're too far, too cold, too devoid of resources, but they'll always fascinate us, these frozen relics from the birth of the solar system. these worlds at the edge of forever, they remind us that the solar system is larger and more complex than we often imagine, that there are still mysteries to uncover and wonders to explore, even billions of miles from home. We've journeyed from Mercury, scorched by the sun's fury, to the icy darkness of the Kuiper Belt, exploring each planet and what existence would mean on these alien worlds. The conclusion is inescapable. Earth is unique, precious, and fundamentally special in a way that's easy to forget when we're caught up in daily life. Every other world in our solar system wants to kill you. Mercury will bake you by day and freeze you by night. Venus will crush you, roast you, and corrode you with acid clouds. Mars will freeze you, suffocate you, and irradiate you. The gas giants will compress you into oblivion, or cook you in their metallic hydrogen depths. The ice giants offer supersonic winds and methane clouds at temperatures barely above absolute zero. The distant dwarf planets are frozen solid, dark, and impossibly far from the sun's warmth. Earth, by contrast, has liquid water covering most of its surface. It has an atmosphere you can breathe without equipment, with oxygen produced by billions of years of photosynthesis. The temperature range is moderate, allowing water to remain liquid across most of the planet. A magnetic field shields us from the solar wind and cosmic rays. An ozone layer absorbs harmful ultraviolet radiation. The day length is reasonable, supporting circadian rhythms evolved over hundreds of millions of years. The gravity is strong enough to hold a thick atmosphere, but not so strong as to make movement difficult. All of this is the result of countless factors aligning just right. Earth's distance from the Sun, its size and mass, the presence of a large moon to stabilize its axial tilt, the timing of impacts that delivered water and organic compounds, the development of plate tectonics that recycled carbon and maintained a stable climate, and eventually the rise of photosynthetic life that transformed the atmosphere. Remove any one of these factors, and Earth might be very different, perhaps uninhabitable. This doesn't mean humans will never live on other worlds. We can build habitats on the Moon or Mars, underground bases to shield from radiation and maintain pressure and temperature. We can construct rotating space stations that simulate gravity. We might even terraform Mars over millennia, thickening its atmosphere and warming its surface until it becomes a second home for humanity. These are all possible, in principle, though enormously challenging and expensive. But living on other worlds will always mean living in artificial environments, small bubbles of Earth-like conditions maintained by constant technological effort. It's not the same as walking outside and breathing the air, feeling the wind, seeing a blue sky. Those simple experiences taken for granted on Earth become impossible luxuries anywhere else in the solar system. This journey through the planets should instill both wonder and caution. Wonder at the diversity of worlds in our solar system, each with its own character and mysteries. Caution because it shows how rare and fragile habitability is, how many things must be just right for life to flourish. As we develop the technology to venture beyond Earth, to send missions to Mars and the outer planets, to establish permanent human presence in space, we should remember what we've learned. Space is hostile. Other worlds are dangerous. Survival requires meticulous planning, robust technology, and constant vigilance. But humanity has always been an exploring species, driven to see what's beyond the next hill, across the next ocean, on the next world. The solar system is our playground and our laboratory, a collection of natural experiments showing what happens under different conditions. Each planet teaches us something about planetary science, about atmospheres and interiors and magnetic fields. Each mission expands our knowledge and our capabilities. Perhaps someday, generations from now, humans will live on Mars and walk beneath its butterscotch sky. Perhaps we'll build floating cities in Venus's clouds, or mine the asteroid belt for precious metals. Perhaps we'll send expeditions to the outer solar system, landing on Titan or Europa or Enceladus. These futures are possible if we invest the time, money and effort required. but Earth will always be special. It's the world that made us, the only place in the entire universe we know for certain harbours life. Every other planet might be interesting, scientifically fascinating, even beautiful in its own alien way. But Earth is home, and there's nowhere else like it in the solar system, or perhaps in the galaxy. So tonight, as you prepare to sleep, remember that you're on an extraordinary world, spinning through space around an ordinary star, orbiting in the narrow habitable zone where temperatures allow liquid water. You're breathing an atmosphere transformed by billions of years of photosynthetic life, protected by a magnetic field generated deep in the planet's core, warmed by a sun at just the right distance, and orbiting a gas giant far enough away to stabilize your orbit without disrupting it. These are the conditions that allow you to exist, to live, to dream about distant worlds. And while those distant worlds are fascinating to explore in our minds and with our robots, remember that the most extraordinary world in our solar system is the one beneath your feet, the pale blue dot that is our only home. So that wraps up our tour through the solar system, exploring what life would really be like on each of these worlds. If you enjoyed this journey through space and science, please consider liking this video and subscribing to the channel. It helps more than you know and allows me to create more content like this. Let me know in the comments which planet surprised you the most, or which one you'd least like to visit. And as always, thanks for watching, and sleep well knowing you're safely on Earth, the best planet in the solar system.